You're recording now. Yes. Yeah. Yeah. Okay, are we all good? I think so, yes. Okay. Okay, I think we're finally all good to get started. Sorry about that. I forgot there was a virtual option. But essentially, if you're here for the Undergraduate Quantum Association's first meeting. Yeah. All right. So again, welcome to our first meeting where we're doing sort of an introduction to quantum mechanics and technology. And thank you guys for being here. I'll say a little bit more about who we are first. We are the Undergraduate Quantum Association, or UQA. My name is Jade. I'm the president of the club.
I'm Neha. I'm the marketing chair of the club.
I'm Jacob. I'm your treasurer.
Yeah. So our goals are to be the university's hub for students interested in quantum. And you don't have to wait until you're a grad student or a postdoc to get interested in quantum computing, or wait until like your third job to realize that, you know, in software development, there was actually this cool stuff you could do in quantum. That's why we're here. We're here to show you what you can do while you're here and help you get ahead in the field, essentially. So including that, you know, in addition to that, we foster a welcoming community of students interested in quantum. We host enriching professional and social events, connect students with UMD's awesome faculty and research for quantum, and be a resource for students who want to learn more. Our past events have included things like going on a tour of IonQ, which is a quantum computing startup that came out of the University of Maryland. We've also hosted the quantum computing track of BitCamp, which is a large hackathon here for the past 2 years, and so we're planning to do it again. And we've also held an international conference for undergraduates called the SQUID Conference. It stands for the Symposium for Quantum Undergraduate Inquiry and Discovery, which was co-hosted with Yale, UC Berkeley, UT Austin, and a school in Turkey. Essentially, we all contributed about like 3 student researchers that all presented on a virtual platform. And that was really cool. But I want to say a little bit more about quantum at Maryland and what makes it super exciting that you're here of all places. We have about like 8 different quantum centers here. We're a top 10 institution in the world for quantum technologies. We also have a CS quantum track for those in computer science major. That can be one of your specializations. There are a lot of ways for you to get involved in quantum here through research, through anything. I mean, really, we're a really great place for quantum in general. So if you have any questions about that or things like that, you feel free to ask after the meeting. And we'll conclude the meeting by talking more about what our plans for the semester are and more resources that you can use and look up in your own time. But we hope you stick with us for the rest of the semester because we've got a lot of fun events planned. We've got a lot of like learning events, but also just discussion-based ones so that people can really get to know each other in this club and form a group of, you know, peers and colleagues, you know, when you go to a conference, like say you'll know somebody there or whatever, but also just that you can form friends here. This all kind of leads up to, at the end of the semester, we're going to be hosting a quantum career fair. So all of the stuff that you've learned, all of the new people that you've met, you can leverage all of that when you meet professionals at like the quantum companies that will be invited to the career fair. So we hope you stay with us the whole semester. Yeah. Okay, so I want to start off with a very like overview, broad question of like, what comes to mind when you think of quantum? Like, what brought you here in the first place? Like, why is this interesting at first glance? I'll take a couple volunteers. Anyone want to answer? There's no wrong answers. Yeah? Small. Very true. Okay, small.
The subatomic worlds.
Awesome. Yeah.
Music question.
Yeah. All that cool stuff. Yeah.
Weird math and handling.
Yeah. Sometimes hand waving involved, but yeah, lots of math, I guess.
Probabilistic mechanics.
Probabilistic mechanics. Okay, yeah. We'll talk about that today too. Anyone else? Yeah. Qubits. Okay, cool. On the quantum computing side, yes. That's a new way to leverage information.
The wave particles.
Oh, yes. Another awesome phenomenon. Oh, yes. Ant-Man. Oh, my goodness, Ant-Man. I love that you brought that up. Okay, yeah? The uncertainty principle, is that what you said? Okay, yes. Another very cool thing. Yeah, we're going to talk about all these things, actually. And to address the person in the back there that said Ant-Man, I think you'll enjoy this part, right? So yeah, maybe some of you guys think of Ant-Man or like the many worlds interpretation of quantum mechanics, you know, a la everything everywhere all at once when you think about quantum. And I would say that maybe these movies are taking science fiction a little to the fiction side. Because I actually was talking to a professor recently who, when I asked her what she thought of like Ant-Man Quantumania, she said, well, the quantum realm was a little bit more microbiology than physics, but I guess it'll get people interested in the subject. So I guess that's one perspective. I would say it's not very grounded in what quantum physics actually is, but it's still a fun guy, you know. Paul Rudd's great. I mean, who doesn't love him, right? But some of you were also saying things like more like this, along these lines, like we think of quantum computers maybe, or we think of entanglement, where you can have two particles that can be separated to the ends of the universe, but when you measure one, you'll instantly know the state of the other. Famously by Albert Einstein said to be like spooky action at a distance, or God does not play dead. Stuff like that. So maybe all of these things, maybe a combination of some of these are what you think of when you think of the word quantum. Let's see. Before we get into the nitty-gritty of like things being small, of wave-particle duality, I want to talk about what's exciting about this new field and why you guys should care and should stay and learn more throughout the semester and the rest of your time here at UMD. Is the potential, right? We're looking at having revolutionary discoveries in biology and pharmaceuticals through quantum computing or quantum simulation, to encryption and security through quantum cryptography, and essentially the possibility of a quantum computer, if it were to be ever built that big, to break RSA encryption, which, you know, underlies all of our secure communications today. We're a long way from that, but that is, again, the potential. The potential to optimize your financial portfolios and do things related to business in the stock markets, you know, if that interested you. And then also climate and atmospheric modeling. There are a lot of variables that go into atmospheric models. So if you had a quantum computer, the thought might be, oh, maybe we can simulate the atmosphere better on a quantum computer. And there's countless other possibilities in quantum sensing too. That's how GPS works. So if you ever wanted to have technologies related to gyroscopes and GPS and a lot of other things, especially like cancer detection, those all have to do as we get smaller and smaller. Love the person who said small. Those things all behave quantumly on the quantum scale. So that's why quantum anything is going to be important in a lot of up and coming fields.
Oh, I also want to mention for finance, one of the algorithms that we use is called the variational quantum eigensolver. Basically, it's they're optimization problems, right? And so when you have stocks, what you want to do is you get all of them and you look at their history and you weight them against each other and say, okay, how do I maximize my risk and reward? These are essentially the same problems, the NASDAQ problem or like the traveling salesman problem. Essentially, so through my internship, I have access to the IonQ computers. So cool, so this way. I use VQE to optimize my stock portfolio and lost 10% in around 6 months. So yeah, everyone clap. Thank you. Thank you. Okay, moving on.
And Hannah got her start at BitCamp, that quantum computing check that we ran. She got interested and now has had internships and research projects in quantum that she likes. So yeah, that she loves. I don't know.
Yeah,
like,
I think all of us are involved in some form of quantum research, like through UQA, or at least like exploring that.
And you already met Neha, Jacob, and myself, but if you three could introduce yourself, because you're also in leadership, please.
We just came back from class. I'm Neha. I'm a senior physics major.
I'm a senior physics major too with a CS minor.
I'm a junior.
What are your names? Sorry, I didn't get that part. Yeah.
I'm sorry, pick me up that.
What's your name?
I'm
Hi, sorry. I'm Dhruv. I'm a junior physics and mechanical engineering.
All right. So yes, back to the slides. Essentially what we want to do though is stop talking about the future and travel back in time via whatever means you want, your DeLorean or your TARDIS, and go back to the 1900s, to the very beginning of quantum theory. It's actually kind of cool that it's only like 120 years old. And today what we're going to do is give everyone a strong foundation, or at least exposure to quantum mechanics, some of the key ideas in quantum mechanics, so that then in our future meetings, we can all talk about various things. When we have speakers come in, you'll have some like just basic knowledge of anything that they might be talking about. We'll just hope to get that grounding here today. And if there's any questions at any point, please let us know. We're all here to help, and we're all learning together. So yeah, nothing is off limits or whatever. Any questions so far on the things that I said about UQA, about the potential, about what we're going to do? Awesome. Okay. So with that, for the rest of today, we're going to talk about what quantum mechanics is, applications of quantum mechanics. So we'll talk about quantum computing and quantum sensing after we talk about mechanics, resources to learn more, and also getting involved in quantum research at the end. So this is the quantum mechanics overview. We're going to touch on these 5 principles that are really cool, really important. By no means touches everything. Like there's so much more, but we just pulled out a couple ones that we wanted to highlight. We have particle wave duality, wave particle duality, the fact that energy is quantized. We have the uncertainty principle. We have the fact that probability is probabilistic, and then superposition and entanglement. And I think almost everyone said like all of these things here. So awesome.
Yeah, also everything we mentioned here, we really scratching the surface just to give you guys like a starting point. So you just catch like the keywords and go read more if you're interested.
Yeah.
Or ask us. If you don't mind.
Yes, be sure to ask us a question.
Okay. Let's start with the Bohr atom. The fact that atoms have fixed energy levels, something you probably saw in high school chemistry and then physics. Basically, when you go really small, energy is no longer on a continuous spectrum as we would expect to see. So up here with us human beings, you would say, oh, I can have 1.5 joules of energy, but I could also have 1.51 joules of energy, and every value in between that is continuous. But at the quantum scale, there are atoms, and those electrons inside the atoms can only occupy a discrete number of energy levels. They can only be at certain values, essentially. They cannot occupy a continuous range of energy levels. They can only jump from one level to the other. An electron moving from a high energy level to a lower one will emit a photon, particle of light, essentially. And an electron moving from a high energy level to a low one will emit. Does that say the same thing? They do. Okay, well, sorry, the other way, low to high, it will absorb a photon, which is, again, energy, particle of light. Yeah. Okay. So this is the beginning of why things are different, why things are cool. They're not continuous like us, essentially, on the macro scale. Micro scale means things are quantized, which is where quantum even comes from. I think you're set to do the rest of, or the next few slides. Yeah.
Okay. Well, and so one thing I want to clear up about the Bohr model of the atom. So we have all these drawings right here, right? And if you think of what an electron cloud looks like, maybe that's what you conceptualize, right? You got yourself your nucleus, you got yourself your little electrons going around, but they don't follow this fixed path. It's a good model, but in reality, what you actually have is you have your nucleus and then like a dense like cloud of just electrons moving around. And so the next thing we're going to be talking about is the Heisenberg uncertainty principle. And so the way this works, I'll try to explain it on a macroscopic scale. And this isn't quite the mechanics of like what's going on, but it's a good enough example. So imagine like you're driving a car down the road and you want to know how fast it's going and where it is. In the quantum realm, you can't actually know those two things because any measurement of the system will interfere with what the actual measurement is. So for example, so let's say you want to measure the speed of the car and you have yourself like a little ray gun and it passes through and you say, okay, it's going X amount of miles per hour. But then you can't know where the position is. In real life, yes, you can. In quantum, you can't. Because if you want to know where the position is, what you'd have to do is you want to make a wall at some point in X. And then the car, when it runs into it, it loses all momentum. It has a fixed position. You go, okay, now it's here. And so in the quantum realm, this is basically what making measurements does. Because, so for example, if you want to observe an atom of something, you can't just like shine a flashlight, right? Like the photon, it would like the energy states, it would like hit the atom and change whatever state it's in. And so when you're taking these measurements, there's always a level of uncertainty. And so position and momentum are reciprocal spaces. And if you're an engineer, then K-space, reciprocal spaces are all about the same thing. And so these are defined by the Fourier transforms of each other. And so position and momentum always have inverse relationships where the more you know about one, the less you know about the other. And here's like one of the most important founding principles of what governs quantum mechanics and why these particles behave the way they do. Oh, actually, I'll also draw a little picture. So if you're not familiar with Fourier raise your hand if you guys have seen like Fourier transforms at all. Okay, cool. So like a little over half, I would say. So if you guys are familiar with the Dirac delta function, it's just a function where you select one particular value of x, and then it spikes up and it has a width of like 0. So it's just this. And then if you take the Fourier transform of that, what you would get is a line, because this just tells you no information about the system at all. You are 100% certain in what, let's just say this is position, and what the position is, so you are 0% certain. There's now an infinite range of momenta that can correspond to that position, right? And then if you have something like a square wave, like this, then your reciprocal space or your Fourier transform would look something like that. So towards the end, these probabilities get lower, towards the middle, the probabilities get higher, and how generalized and how pointy that is going to depend on how generalized and how pointy this is. So the more pointy one is, the more general the other one is, and vice versa. This is really bad artwork. Okay. Oh. Cute.
Fancy.
Okay.
Wait, I wasn't doing this.
Oh, you're not doing that one? Okay. Okay, so what's a wave function? Everything you know about a wave function, or about a quantum state, is given by its wave function. So the wave function, typically you see it written in some form like this. Here is just the wave function of a state prepared in where the probability is half spin up and half spin down. If you don't know what spin is, that's okay. It's just something that an intrinsic property that all particles have. And so what this is saying is there is a 1 over square root, that's the coefficient, and so the probability is the magnitude. So the probability that it's in the plus state is 1/2. The probability it's in the minus state is also 1/2. Why is my handwriting so bad on these chalkboards? Is this legible to people?
Yeah.
Cool. Okay. So that's what a wave function is. And this seems a little bit contradictory to what we understand about macroscopic objects, because if I say there is a probability, there is a not 100% probability that I am standing right here. If you guys have ever seen those like weird TikToks about quantum tunneling or quantum teleportation, that is what they're referring to. They're basically saying there is like a 0.0001 chance that if I jam my fingers through this desk, it will go through. It's stupid, and like, you know, it's not something that's realistically going to happen on the macro scale, because there's like millions of atoms where my fingers are, and every single millions of those atoms would have to align with the desk in such a way that it goes through. This is possible on smaller scales when you have like one atom slipping through. That's very different from like the macro scale that people talk about, where you like throw something and it goes to the wall. But yes. And so if you guys have also heard the phrase consciousness causes collapse, what that's saying is consciousness of the system, or any measurement of the system, induces a collapse of the wave function. And a collapse of the wave function means that it goes from this probabilistic state to a definite state. You pick one. You either pick plus or minus, or whatever your other states are. Consciousness causes collapse.
And consciousness in this like context is measurement.
Yes. So consciousness is any form of measurement or any form of observing the system. Any questions? Is very like, this is kind of the heart of what. Go ahead.
When you throw a ball at a wall, so
Yes, still thinking about
will like a few atoms of the ball go through the wall, but like nothing,
No,
just
so
a few
even-
tiny bits of it.
Well, so one atom going through like another like lattice or whatever, that in and of itself, that one process is the one that has like a 0.0000 whatever. Like we actually, if you guys take 401, one of the homeworks your professor will probably assign you is actually in quantum tunneling, because there are equations and there are models. And so the question I think last year was something along the lines of like, if you have like a softball that's like 2 inches in diameter and like these are the conditions, then what are the chances that that softball passes through another object? Dude, the answer is like so ridiculously, it's like 1e and like negative like 50 or something.
What about
It's
like tiny
ridiculous.
bits of the ball, like
So
Again, that's just for one atom. So
let's say it's
go for it, yeah, actually.
I should add though, like, we talk about tunneling in this macroscopic sense, like this sci-fi thing, but we use tunneling in a lot of applications. Your phone has extra, what we call ancillary bits. It has extra bits in it because information from photons in your phone can tunnel between different wires. And so we have like, if you study electrical engineering, this is a legitimate concern for when you design boards, because photons can go from one waveguide into another waveguide. They can like physically teleport, and we use these in labs as well. And so, as much as this is a quantum thing, it's something that we've known for a long time and we physically use when we design devices.
Yes, I just want to emphasize, it is kind of silly to talk about in the macroscopic sense, but yes, you're 100% right. There's a lot of interesting applications in the microscopic scale with those.
You said conscious and
See, that's a great question, because that is, again, so if you've heard of, so all the thought experiments you've heard of, the Schrodinger's cat or like the tree falling in the forest, they are asking the same question in quantum mechanics. And so it is asking, are we defined by the consequences of what we produce, or does it exist in a vacuum on its own? So in the case of Schrodinger's cat, the philosophical question it's asking you is, without opening that box, without observing it, where that cat has a 50-50 probability of being alive and dead. So we know it exists in one of those states, right? So does it exist in a vacuum without us opening the box? Can we say with certainty that it's either in one of those states? Like, we can't, right? It's like, you have to, that's kind of that's like the nuance of it, right? Because it was meant to be an absurdist take of the Copenhagen interpretation of quantum mechanics when it was first proposed by Schrödinger. But now we actually use it as like an example of how it works, because it's kind of funny. But we say that the cat is both alive and dead until we open it, because once we measure the system, now it becomes definite. And again, I understand this is a kind of a nebulous concept, but in this case, just take any form of consciousness to be measured, or just any kind of observation
Oh,
of
like
the system.
interaction.
Right.
So if this plant in any way will interact with the quantum system, say like in any way, like I don't know what could the plant do, but if it interacts in any way with the quantum system, that could count as a measurement and will collapse the wave function.
You don't actually want to know.
Like one,
Because
yeah.
You have, like, let's say you have a state, like describe it on the board, say some electron traveling down some wire with spin up. And there's a defect in that wire that would have constituted a measurement. That is for the state.
Yeah, so I don't mean consciousness by like, oh, like I observe it happening. I mean, it interacts with another part of the system that forces it to pick a definite state rather than a state.
Yeah, like
of-
consciousness cause collapse is more like a buzzword for quantum. It's not
But like, I think it's a
literally.
good phrase. I like it.
I'm kind of against it. but
Really?
Sure. Yeah.
Well,
Because-
because consciousness is like just the realization of the system. That doesn't require the participation of a human observer. It just requires the interaction of two systems. So like an atom hitting like a wall or something like that. That is a form of consciousness, because that atom has been realized by the greater world. And now there's a consequence that is forced it to pick a state. Does that kind of make sense? Okay, any other questions?
We have a question from Zoom asking if we
Sure.
can force tunneling, or if we just have to put forth conditions and hope it happens.
That's a Dhruv question.
What was the question?
Can we force tunneling, or do we just have to put forth conditions and hope it happens?
Oh, I love that. Okay, so when it comes to, when it comes to tunneling, the idea that you can have a object on your nanoscale going from one thing to another, it's not something you force or don't force. It's something that, if I have two electrical wires that are really close to each other, the probability that my electron will go from one wire to another is much higher than if they're further apart. So in photonics, for example, when you have wires carrying light, you have these things called couplers, which change how far apart your wires of light are. So a 99-to-1 coupler, for example, means that 99% of the light that passes through one wire continues to pass through, only 1% of that light goes into the other one. There are other couplers, a 95-to-5 coupler, which bring these wires even closer together, a couple micrometers apart, where 5% of that light goes from one wire into another. So you can control how much gets teleported and how much gets tunneled and how much does not. Good question. Yeah.
That is a good question. Yeah, unfortunately for me, my research has like nothing to do with hardware, and so I don't know any of those kinds of things. But okay.
So
Yes, go ahead.
just something to like emphasize, talking about like uncertainty principle and wave function. these like uncertainty and also the probability is an intrinsic property of the quantum system. It's not because we human can't see it. It's not like it's so small we human our like detectors or our experiments can't see. It's actually even if no one looking, oh probably when no one looking is probabilistic.
Yeah,
This is the argument of quantum mechanics.
oh,
These are just like some wave functions and energy.
Just
levels.
an
Yeah,
example.
that's all that is.
Okay, a wave function is basically a function that describes where you're gonna find a particle. Now we said that particles are probabilistic, so for every observable, every measurement you can take of them, we can't tell you exactly what you're gonna get. We can only give you a certain probability, and that is described by that particle's wave function. We'll show you the equation later from which you can solve to get these. But there's a lot of them, and they usually look somewhat sinusoidal.
Yeah, it just to emphasize, like this show you that these are the wave functions which has some amplitude. If you like square that wave function, you get the probability. This is what's showing. It's showing the wave function and their probability density, what we call that square of the wave function.
Oh, okay. So this is the equation which we get them from. This was thought out by Schrodinger. We don't actually have a way to mathematically prove this. We can just say it seems right.
I mean, if you use
We're
experiments,
Right.
experiments so far have been proving that this works.
Yes.
So it's more like we can't prove that wrong.
Right. What else could it be? Yeah. So quantum mechanics is actually the most experimentally verified theory, which is why it's tough to come up with more stuff because it just seems so right to us. So this is the equation Schrodinger came up with. It's actually a combination of a wave equation and a conservation of energy law. And he postulated that you could describe quantum systems with wave equations. Then he plugged that into the conservation of energy and he gets this. You don't need to know these yet, but this is something called the Hamiltonian operator. It tells you the energy of this system, and this relates it to how a wave function behaves when you know its energy. So we solve this equation, and we get those wave functions that you guys saw on the last slide.
Sure. So, yeah, let's take a moment to just pause. We have more popcorn, like 2 minutes. If you wanted more snacks, come get them. But like recap, talk amongst yourselves, come up with questions that maybe like didn't seem clear. We kind of threw a lot of information out there. So just like 6:42 is the longest we'll go. But yeah.
I didn't see a chair, anything like that.
Drew, you're supposed to do okay.
Comments.
Drew, what did you do over the summer? I wasn't here when you gave the presentation.
Okay, 2-minute recap. IBM, for the first start, I worked on these, called qubits. Traveling wave pyramid like this. Basically, you read out, it's really tiny, a couple photons.
Okay.
Quantum limited amplitude. If you read it right, you can only get 1 photon of noise by the uncertainty principle. So that's why it's quantum limited. But the idea is you have multiple qubits. You need to be able to calibrate it well the different qubits, and they're all going to be at different levels of quality. So I was working on different numerical qubits like that, and then like it's fun because like it's implemented on their it's part of the device right now. Mom directs in on every system and runs through that. It's literally called multi-object mode. Doing meetings were like, yeah, Mom is functioning okay. It's like I was working on Montreal, Australia, how to find I loved it. Yeah, it was right as much as possible. It was nice. And then the paper I was working on got accepted. Next week, my talking yesterday was like preparation for for it. So, over the summer, I found out that when we were working on revisions, like the reviewers gave like feedback, trying to get that up.
Oh, I think what you see, so like, yeah, it's hard to find anything you
Alright.
want.
Yeah. For gravity, that's what we're working on. It's a work in progress, but that's the reason why it's hard to come up with equations for that, because you need to find these relativistic equations that also satisfy all the non-relativistic stuff too. I think we're still looking for it. I believe, have we experimentally verified gravity waves yet?
Yes, gravitational waves.
So we've
Yeah.
determined, or we've detected gravitational waves, but I don't think we found the gravitational yet. Yes. That's true.
Okay, get back into it. We only have like less than 20 minutes left. So just to recap on what we talked
So
about,
rude.
the Bohr atom exists. Well,
Um,
named the atom is like the Bohr model.
Can you
after
guys still
Neil
hear us in
Bohr
here? We're not sure.
experimentally Verified that. So energy is quantized. We also talked about the uncertainty
think we can.
principle and how you can't know position and momentum at the same
Okay,
time.
great.
We've talked about wave functions and how
I
they're
think there is,
relativistic.
but I'm not sure.
So now we will go back.
That's pretty
to-
complicated quantum stuff.
You good?
Yeah.
Oh, someone asked a question. We'll get to that in a second, but let's keep things moving. Jacob, are you good to go?
Yes.
All right.
Does anyone have any questions before I start off again? No? Cool. All right, great. This guy again. So this is the double slit experiment. This was done in 1801, I think. So this is a really old, really old, but basically what they did was they took light and they shot it through two slits. Now, if light were discrete quanta or discrete particles, we would expect that to be like the second picture. You just get two beams, they come straight out of the slit and hit the wall. But instead, what they found were these interference patterns, which are consistent with when you pass waves through a screen like this. So say you had water, you had still water here, and you started creating ripples over here. And those ripples passed through the slits, they interfered, they did all that fancy wave stuff, and then they hit the wall. This would be the pattern you would get. And that seemed to be pretty good evidence that light acted as waves. So for a while, they thought it was really just waves. Okay, so before we move on to the next slide, I'm going to give you guys some evidence for why it's also not waves. So there was this big problem back in the early 1900s called the ultraviolet catastrophe. You don't really need to know the information about that, but they had this issue with how much heat these things called black bodies were emitting. And the theory for that predicted that, can you guys give an
Okay.
example?
So the ultraviolet catastrophe with the black body radiation was like the starting point to think about quantum mechanics. Because of that, we need to quantize energy to get the to get it to work as we expected. But I think what the evidence that that photons exist, that light can be particle in a wave, came from the photoelectric effect that Einstein worked on. So in the photoelectric effect, it's about if you shine a light on a metal for like a good amount of time, the light energy will knock off electrons from that metal, creating current. So the thing that was expected that increasing the intensity of light will increase the energy of these electrons coming out. However, this is not what they saw. They saw that it depends on frequency and not on the intensity. Okay, what was depending on the intensity is the amount of electrons coming out. Because if you increase the intensity of light, if you think about as photons, you increase the number of photons hitting the metal and knocking off electrons. And the frequency relates to the energy of the photon, which that's why relates to the energy of the electron. So this was like the first experiment that showed that light has to be quantized and acts that way to see the affect the effect we see from the photoelectric effect, yeah.
Okay, so and this top equation, E equals H nu, is the equation that resulted from the ultraviolet catastrophe. So they figured out that the energies of particles has to be quantized. You have this, which is called Planck's constant, and then this nu here is just different integers. So the energy of particles can only take on like 1 or 2 or 3 or etc. times this h. So cue this guy named Louis de Broglie, working on his PhD in 1924. De Broglie had this idea that because light had these frequency relation, so this is actually the frequency of the light. It's a bit complicated, don't worry about it too much right now. But he thought that he could use these other equations, very simple equations, to relate that frequency to a wavelength, which would seem to put the cap on it that light is a wave. And this is what he comes up with. If you solve these out, you'll get this. So now, not only do we have the wavelength of light, but we also have a way to generate particles with certain wavelengths. Okay. Here's another experiment they had called the Stern-Gerlach experiment. We're cutting over to discretization again. So the Stern-Gerlach experiment was an experiment thought up by Otto Stern in 1921 and then actualized by Walter Gerlach in 1922. Basically, particles have this thing called spin. Has anyone heard of that before?
Yeah.
Okay. It's pretty, they just say spin is spin when you look it up, but what spin is, it's a lot of things. What it most basically is some sort of intrinsic angular momentum that particles have. And this was throwing off calculations. So if you had this big system, they would put it through a magnetic field and it wouldn't work like they thought. So they wanted to figure out, what is the spin? Do particles really have it? And are our equations right now wrong? So what they did was they came up with this experiment. They shot these silver atoms, which were unique because they had a single valence electron that had no orbital angular momentum. So it would only have spin through it. And they passed it through a magnetic field. So this would cause the atom to be deflected based on the spin of that one electron. So they could measure that. So they passed it through, and what they found was that they only got 2 values for it, up and down. And those had other values. I won't go into that too much, but no matter what they did, no matter how they prepared the atoms before, they would only get these 2 values.
The Stern-Gerlach experiment.
This is, I just put this video for visualization purposes because it has really good visualization. So basically the spin is related to the intrinsic magnetic moment too. That's why it's affected by the magnet in the experiment. So basically what it's showing here, this is, you could think about spin of something like this, of like a ball that's spinning, basically. It's a vector. And then, oh, sorry. How, what? Why is it not? Just this point, yeah. So this is like when you shine these atoms, they have different spins. It's like this arrow, but once it goes into the magnet, they always only come out in 2 different directions.
Because like traditionally, so you can think of them as just like dipoles, right? They have and you have an inhomogeneous magnetic field, and so you'd expect if you have like a little dipole, right, and you shoot it through that magnet, you would get spreads like this kind of, like, so just depending on what the orientation of the magnet as it went in was, you would expect it to come out kind of the same, depending on wherever, like whatever the orientation was. But no, you only got alignments like this. So south, 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 but yeah, so you'd only get these 2 different alignments, which was contrary to what you'd expect based on our understanding of how magnets work.
Why is not this nothing?
Oh, how interesting.
Oh, also fun fact, when they did this experiment at first, they like totally misinterpreted the results. I don't remember exactly what the misconception was, but like they got the right conclusion, wrong answer basically. And then so when they redid the experiment, they did it better. But in the first iteration, they actually like totally messed it up.
I just want to emphasize like how cool that is, because I guess from the room, anyone CS major, raise your hand. Okay, a lot of CS majors. Anyone engineering? Any engineering? Okay. Physics? Any physics? Good amount of physics. Anything else? Am I missing anything?
Just shouting.
Math? Oh, beautiful.
Nice.
Anyone else? Math? Yes. Math. Anyone that isn't math, but anything I'm missing? Yes. Business. Great.
Finance. Main Street, baby, you're gonna be
But-
so rich.
So, but it's just a really cool phenomena, because you might remember from physics, if you have anything that has a charge and you have a magnetic field, it's going to go in one direction or another. So the fact that they took something with no charge and it still moved in a magnetic field, and it moved to specific locations every single time, is pretty remarkable. And so we use this in quantum mechanics for the idea of superposition. Because if I send 1,000 particles that I don't know its orientation of, and I send it through this analyzer, I could end up in a situation where half of it are up and half of it are down. I could also end up in a situation where maybe 3/4 of it are up and 1/4 of it goes down. That's the idea of superposition, that we can prep these particles. We have the technology to prep these particles so that when we send a bunch of them out, we can send them with varying probabilities. And so when people say superposition is the fact that something can be both a 0 or a 1, or both spin up and spin down at the same time, this is what we really mean. And we exploit this in computing, we exploit this in sensing in many different ways. The gyroscopes on the James Webb Telescope and other telescopes use the spin of a particle to calibrate itself. And so this is, I guess, what the idea of superposition is. We've been using it on MRI machines to make these devices. And so within quantum technology, there are 2 stages. You have the first quantum revolution, the second quantum revolution. The first one uses superposition. It uses this property that we've been able to control very well for the past 2 to 3 decades. But this other thing that you've probably heard of is entanglement. The fact that I know the state of one particle if I know the state of another one. So the analogous example will be if I have 2 particles that are entangled. If I have, let's say, 2 neutral particles, one spin up, the other spin down. If I know that one of them, if I have them entangled and I send them across to opposite sides of the universe, and I measure one of them to be spin up, I know for a fact that the other one is going to be spin down. Even though they're really far apart from each other and they have no intrinsic connection. You might think this isn't that special, right? So I could, let's say I had a red envelope and a green envelope, and I didn't know which one I gave you, and you went to the moon, and we both checked at the same time what envelope we had, and there's a 50% probability I have the green one and a 50% probability you have the red one. That's sort of analogous to entanglement, except once I've given you the envelope, what you have doesn't change. With entanglement, I can send you an entangled particle. I can keep one to myself. You can go to the moon, and I can manipulate my particle in different ways that affects what your particle is. And that's what's really special about entanglement. So we use entanglement in really clever ways. And one example is computing that we see over here that I'll get into in the next slide. We also use entanglement for sensing, as I said, gyroscopes that don't need to be calibrated to begin with. So you have almost a perfect measurement every single time. We use it in materials, as I mentioned, we mentioned earlier with the circuit boards in your devices. Simulations as well. In physics, we're very interested in simulating nature. And so we can use these properties with computing as well as just hardware itself to simulate different properties as well. And then communication and cryptography kind of go into the realm of computing. The idea that I can send you something in the only real way that is truly secure. But first with computing, Oh, yeah, with computing, these particles that we call, these particles with spin, we call them qubits. And the idea is that in a traditional computer, I have a bunch of bits that represent information. These bits can either be 0 or 1. And once I've made them 0 or 1, they stay at 0 or 1, unless told otherwise. With quantum computers, I can use qubits. And instead of telling the bit, you should be a 0, you should be a 1, I can tell this bit, you should be somewhere between 0 and 1. So that I can now leverage the fact that it's in a way both 0 and 1 for my computation. I can then also say, wait a minute, I want this qubit to be entangled with another qubit. So typically on computers, I will set my bits to different numbers and that's it. They don't communicate with each other. I can get my qubits to communicate with each other. This opens up a huge new paradigm of computing that has a lot of possibilities in the distant future, admittedly, because our quantum computers are not as robust as they need to be to show real potential. But it's incredibly promising, and people have been working on this for the better part of 2 decades. And so a really famous example that is sometimes overused is Shor's algorithm. So currently, when we have data, we encrypt data with very large numbers. And to figure out how to decrypt data, you need to know the factors of those numbers. So if you know the factors of these very large numbers, you can find what that information is. So we make really long strings of digits that take normal computers almost 2,000 years to decrypt, to encrypt our data. But back in, I think, 1998, Peter Shor, a mathematician at MIT, figured out that, hey, using this particular quantum algorithm, you can find factors of a number very rapidly. So you're able to, with a large enough quantum computer, by large enough, I mean hundreds of thousands of bits. We're currently at the stage of only hundreds of bits. You can decrypt data, which is a huge risk. It's why people put a lot of money into quantum in general, to be able to alleviate that, that threat. So this is one example of how we're using superposition, we're using entanglement in the paradigm of computing to solve problems. We have algorithms now. People are working at NIST on quantum safe algorithms that Shor's algorithm cannot easily factor. And so that's one example of that. Just as a brief overview, anyone an electrical engineer by any chance? Okay, a little bit. So with normal computing, we have gates we apply on our bits. In quantum computing, we have gates we apply on qubits. And typically, if you see this diagram, if you see a block on one wire, each wire represents a different qubit, and the blocks represent what you do to that qubit. If you see blocks that span multiple different wires, so this little plus sign with a dot at the top, those represent gates that manipulate 2 qubits at the same time. Those use entanglement. These H gates use what we call superposition. But that's one application there.
Okay, just first it's 7, so if you need to leave, you can leave.
Yeah.
We will continue if you want to stay.
We
Except
only
if
have a
everyone
little more
leaves,
left.
but
It's
yeah.
just of the applications and then a couple of UMD opportunities and some.
I think it's like only few slides left, but yeah.
Like 5, 7 minutes left.
They want to move it. But anyway, so the other application we're gonna focus on kind of is quantum sensing. So quantum sensing could be more relevant for people like in engineering, chemistry, biology, physics, because the idea is that these quantum systems, these quantum properties, can also use as detectors or sensors to make precise measurements. The thing that a quantum system can be affected by a lot of factors and fields. So if you want to make a sensor for magnetic field that is extremely precise, you could make your own, like do the study, do the math, and make a quantum system that if there is a change in magnetic field, you get some sort of output. It could be a change in energy, like a photon or like an electron, and then this way you could sense the magnetic field. So this can be much more sensitive to classical sensors that we have, and then there's also application in medicine, proton modeling, and geographic exploration and everything. So there's like some platforms that I would say like atomic clocks can be considered quantum sensors. as they give precise measurements of time. And another is quantum crystals, squeeze light and trap atom and ions are also used in sensing applications. This is just a quote table I found in a literature review. I cite this with like a link to it. But this is show all the, not all, but a lot of types of implementations of quantum sensor and like this is like the medium and what is sensing and the measured quantity and like how it works. And
All right, no worries if you're feeling overwhelmed. This was us trying to compress like everything cool about quantum within an hour, and we did go over, so you know how interesting it is. But next week, we will be sort of going in more into depth about these things. We will send these slides out if you'd like to look at everything in your own time. So next week, we're going to be looking at this paper called Quantum Computing in the NISC Era and Beyond. There will be pizza. It'll be, we're gonna provide this paper, I believe, before the meeting, so
Yeah, you can
people.
find it online.
Yeah, so you can look at it in your own time if you'd like to get an idea of what we'll be looking into, but you can also come in and just listen to what people have to say if you're not 100% sure.
It's a very readable paper. John Fresco is like one of the foremost people in quantum information. He's very cool. And he's done a lot for quantum information, I should say. I don't know how to say that, but like, yeah, this paper, we'll send it out with a link publicly available.
Yeah, you don't need any real technical background for the
No,
paper either.
He
It's
writes
very
it like
light.
he's talking to you, so it's
Yeah.
like very close.
All right, and then this is a course. What is this course offered by?
Qubit by Qubit.
Qubit by
Sure.
Qubit.
You could go.
Yeah, sure. So
No.
this is a course taught by an organization called Qubit by Qubit. It's a year-long course on intro to quantum computing. It starts at the high school level and above. So it's in terms of like, if you're worried about, your math levels, you shouldn't be. It's incredibly introductory, goes through both some quantum mechanics and quantum computing. Even though there is a cost to the course, if you're a student, you can apply for the scholarship and you're pretty much guaranteed it because we're students. I have taken the course, Jade has taken the course. It's a fantastic introduction. It's taught really, really well. They also do lab tours from groups at both Maryland, MIT, Duke. Cool way to also see the community and everyone that's doing it out there.
It's like a 2-hour commitment a week, and
Yeah.
the thing that's like just special about it is that they're very well versed in education for these things. So they've had years of practice. I think it's in like its 4th or 5th year now, and it's very accessible. I think if you want to go deep into quantum computing specifically, because we try to cover a broad range of things, and we're not going to, particularly focus on one thing. So quantum computing specifically, like this is a great course. I think it also, gets people excited about it, which I think is the good part, and also shows you how you can, just learn more.
Also, if a lot of like the UQA community are signing up to the course, you guys could like, I don't know if it has homework or like practices, you could do this stuff together, like discuss the lectures and just have people taking the class with you.
Yeah,
It's a
honestly,
1-hour lecture, 1-hour lab, so 2 hours a week. It's pretty simple, and like the quizzes are not too bad. I would
Yeah.
say.
if enough people like take it, I guess we could like make a channel in the Discord or something so you guys can like make like study group
Is everyone in
like
the
that.
Discord by any chance? Okay, cool. If you are signing up for it and you're running through any issues, please message us. Yeah,
Oh, also
Yeah,
you
we
get
could
a
help you.
certification from IBM when you complete it.
Yeah.
Which is awesome.
Yes, and we can send out this information as well. And Hannah, I think.
Yes, okay, and then so the other thing I wanted to mention was the Math Quantum Information Science Fellowship. So this is an NSF backed fellowship and it's really great because it's fully paid. These 2 QR codes, basically there's an interest meeting next Thursday at PSC. You'll get to meet the PIs and other grad students, faculty, and undergrads are going to be going. So that's the RSVP form for that. You don't need to, it's just like a head count for the food and stuff like that. And then down there's the Math Quantum website where it'll tell you all the benefits. So basically you get assigned like a research project where you'll be using really advanced math techniques to solve advanced information science research problems. So like different ways to manage the data, like developing quantum algorithms. I think there's like a lot of cryptography elements as well. It lasts at least 1 term and it's amazing because you get paid so well for this one actually. You get paid $2,500 per semester for spring and fall, and then $1,000 per conference you attend or workshop. You're expected to attend at least 1 per semester, and then over the summer I believe it's $5,800 for 8 weeks of work. And then you're also expected to do the one conference, and then you also have to take part in their research writing workshop. So if you guys are interested in any of that, this is especially open to math majors, but physics and CS are more than welcome as well.
And engineering
And it doesn't, by the way, the fellowship doesn't assume any prior knowledge of having quantum knowledge at all.
Well,
It's just if you're interested, is what the wording is.
Yeah, I think kind of do expect, well, because it's Daniel Serrano, Andrew Childs, Anil is helping run it, so these are all like the quantum people. I think they expect some level of quantum background, but from what I understand, they're all the advanced math stuff they want you guys to do, they will teach all of that. I assume a background in quantum would be nice, but don't let that deter you if this is something you're interested in.
Yeah, I mean, at least show up to the interest meeting and see what they have to say, and ask them directly if you have questions.
Yes,
Yeah, of course.
so if you go to the website, it basically says if you can't make the meeting, email Daniel and he'll schedule a one-on-one with you or answer your emails.
Yes, also you should, what's it called, for the RSVP, I think there's an option that says you can't go, just do that because it'll sign you up for their mailing list, so yeah.
So this is a really good way to get involved in quantum research right off the bat. We'll be providing like other resources for how to do it, but I mean, this is a great opportunity.
Yeah, this is in the opportunities channel in the Discord, so I think Hannah already posted that. And yeah, we are going to be creating a resources page with a lot of these resources on, so that way, if you're feeling overwhelmed and you want to look at things in your own time, you have like a little pamphlet or brochure to sort of go through things step by step. So these are all really good resources and really fun resources that you'll enjoy. And come to UQA because we are here also to help you discuss things and learn things in a more casual environment. And if you're interested in quantum research, just look around. A lot of professors, UMD has a lot of professors that are interested in quantum. There's QLab, JQI, and stuff like that. And even if you don't feel like you're qualified to do research, you can at least go talk to them. And a lot of them are really willing to talk to you about their research. So if any of that interests you, you should just contact them.
Yeah, so you could just look up their research. They probably like you could find it in their like research center website or the UMD physics or CS or engineering websites, or even just if you find their group website. Read a little bit about the research. If it interests you, make a list first of all the professors you're interested in. Email all of them. I will tell you, not all of them will reply. Not all of them will be like, oh yeah, come to talk. But at least some of them will, and it would be a great opportunity for you.
And also just like talk to people, especially people here, like people constantly bring in like their friends into research labs because like hiring is annoying. You don't want to like slog through like dozens of undergrad applicants. Hannah, another Hannah, she brought in Neha into the Ivy lab, and so they're working on the electron ring. You guys are doing humor.
Yeah,
right? Yeah. So the electron ring is what they're working on now. I work in the National Quantum Lab. Drew works for the National Quantum Lab. We both got like summer internships through that. I worked for Paraton. Drew worked for IBM.
I mean, lucky we brainwashed him for
Literally, he was
amazing. He added to physics.
So we got him. Okay. But yeah, so like seriously, just like build communities with people and like learn what other people are doing and like talk about what you're interested in. And a lot of times people will have like people be like, hey, like these grad student in my lab is leaving, like would you want to apply for like things like that, So I think people consider science to be very individual pursuit at times, especially on like the level we are at now. But it's most definitely not like finding like a good space for yourself in like the physics community is really important.
So yeah, that ends our meeting. We're like 10 minutes over, but thank you guys so much for coming, and please come to our meeting next week if you're interested in learning more. It was really great to see all of you here. So thanks again. If you have any questions, come up to us at the end.
You could take some snacks when you're
We have more popcorn, more crackers. Yeah, hope to see you next week. Thank you guys.
Dude, how many people?
Thank you to our people on Zoom. Hope you guys had a good time. With the Discord link and everything, we'll fix those emails and everything like that. If you're from outside of UMD, that's so awesome. Thank you for coming.
Wait, let me see who's here in the
Some of
chat.
them left.
No. I wish I could see all of them because
There was someone from UMD.
yeah,
There
because
were like
because what's it called?